Today we're going to talk about some energy associated with nuclear reactions. And when we talk about energy, typically we think about that equation that Einstein proposed way back in the day. And it's probably one of the first equations you were introduced to but never used as a child. But before we start talking about E equals mc squared, one thing I want to talk about is that everything here on Earth, including you, the desks, etc., is made up of material from a star that exploded long, long ago. You were actually the product of a supernova. The atoms that came off of that star are the same atoms that make you up right now, which is kind of cool. Now, there are some other particles from different stars that haven't actually made it to Earth. But here's an interesting fact. Even though you're only like 15, 16, or 17 years old, or even older, 14, great. The things that make you up are actually billions of years old. Remember that we don't create or destroy matter, it's just rearranged. So you were probably made up of something that existed long ago. But the things that make you up are not new. They're not unique. They've been around. Okay? They're just being rearranged. So, yeah, I'm sad that Prince is gone. But you are from a star. All right, so nuclear fission. This is actually, and we're not going to do an experiment with nuclear fission in here, sorry. But this is actually the process whenever a nuclear reaction takes place. And you have to have what's called critical mass to actually have this take place. In other words, you have to have enough for a chain reaction to occur. And I'm not going to test you over the mechanism that's involved in this. But here's one of the scenarios that I found or stole a picture from, where you've got this uranium-238, I believe, and it is struck by a neutron. And it has enough force that it actually, when it makes impact with that uranium, it splits apart into a barium atom and a krypton atom. By splitting, or by breaking apart, it releases a significant amount of energy. Not only does it split apart into two new atoms, but it also releases other subatomic particles looking for other uranium atoms to collide with or to split. So what happens is, after each one of these things splits and a lot of energy is released, then bad things happen, at least from the images that we've seen. Okay. Does everybody have the blanks up to this point? Okay. So what I want to talk about today is the equation E equals mc squared. And if you've had physics, or you may have done some problems like this in the past, the thing is that we're going to have this information up here. Okay, that would be given to you. It's just a matter of being able to use it or to manipulate it to get the right answer that you're looking for. So I have two practice problems. Get your calculators out, warm them up. Let's do some fun here. All right, so the first practice problem says calculate the amount of energy in kilojoules that is released in a nuclear reaction when the mass lost, or should say not lost, but changed, is 3 kilograms. So remember that we have this equation here, equals mc squared. That is the one that we're going to use for all of these types of problems. So we have E equals mc squared. And which variable are we looking for? E, the energy. Now the really cool thing is, there's only two variables to solve for. You're either going to solve for the mass or you're going to solve for the energy. Because c, the speed of light, doesn't change. Now it is unique because we do have a square on that. All right, but that helps us to get to this unit here, which is in kilograms meters squared per second squared, which is equivalent to a joule. Okay? So let me move those guys out of the way. All right, so we do have E, and do we know the mass for this? 3 kilograms, so let's go ahead and write that down. So we have 3 kilograms, and then speed of light is given, it's 3.0 times 10 to the 8 meters per second. So when we type this in, or write this in, okay, be sure to show your units, and then put the square on the outside. Now, what type of unit will you have when you multiply all this out? So your unit will be what? Good. So it'll be kilograms meter squared over second squared. That's the value that we should have when we finish here. Okay. Zap that guy. So, how do we type this in on our calculator? So 3 times 3 EE 8, and then there should be a square button on your calculator. Some have an EE. Do you have a TI? Okay. And let's get a value for that. Two point 2.7 times 10 to the 17. Anybody get that? Yeah. Okay. So that's what we have. Come on over here. So that's what we have in kilograms meter squared per second squared. But that's not what the question's asking, is it? What does it want it in? Kilojoules. Okay. So we'll speed that up. So now we're going to do our conversion where we have 2.7 times 10 to the 17. And this is the one time throughout the year that I actually will have more than one division line. I'm going to keep this guy together, meter squared over second squared, because again, none of those are going to cancel out individually, so the whole thing's going to go as a whole unit there. So here's my answer that I got from the previous problem. 1 kilogram meter squared per second squared is equal to 1 joule, and that's given. So that is up here, right there. Okay, and then we need to get it to kilograms, or sorry, kilojoules. So what do we need to do next? Okay, so joule goes here, kilojoule there. All right, Ethan, so how many joules in a kilojoule?
How many joules are in a kilojoule? 1,000.
Good, so it'd be nice if you guys could.
I'm literally already.
Okay, so when you type that in, 2.7 times 10 to the 14, good. And that would be kilojoule. No, you're all right. Now, in this case, you don't really have to do typing the calculation in, but if you're not comfortable, just realize that you have 10 to the 3 here, so it's 10 to the 17 minus 10 to the 3, which will give you 10 to the 14. Okay. But if you're not comfortable, make sure you type it in. Okay. Isn't that fun? Let's do another. All right, number 2, calculate the mass in grams of nuclei that was lost or converted when 3.3 times 10 to the 15 kilojoules are released. So again, we have our E equals mc squared. And this time we're looking for what? The mass. Good. So it's not a bad idea. Rearrange. So we need to get this on the other side. So our equation now is this. Mass. And we'll eventually get to that. What should we do first? Good. Get this to joules. Okay, so we've got 3.3 times 10 to the 15 kilojoules. So kilojoule down here and joule there. What is that? Okay, so 1,000. And let's just keep going. Is there another conversion that we can use here?
Yeah.
Good. So we'll go kilogram meter squared per second squared. Okay. And doing the mental math, which can be dangerous at times. 3.3 times 10 to the 18. And that's kilogram, meter squared, second squared. Again, so what we really have is this right here is 10 to the 3. So 10 to the 3 plus 10 to the 15 gives you 10 to the 18. Okay. Now, we're not done yet, so don't get excited. We now have our, what does this represent? Which variable? E. That's our energy. And if you forget, just remember, oh yeah, we started with kilojoules back here. Okay. So now we can plug that into our equation that we just rearranged. Actually, let me slide it down. Bring it on down there. Okay. So we've got our, so 3.33 times 10 to the 18. And again, probably not a bad idea to keep it together there. And what do we put on the bottom here? So 3 times 10 to the 8 meters per second. And let's square that all up. What units are going to cancel here? Seconds and meters? Squared. Good. So these guys will change because of the square. Now, when typing this in, be careful here. It's not too bad. But 3.33 EE18. You probably should already have that in your calculator, but if you need to retype it. And then divide it. And I would go double parentheses on this. So 3 EE8 parentheses x squared, close parentheses that. What do you mean? What's that?
Can't you just use like the square button instead of the
No, that's not an exponent. If you did 3 square, you're going to do 9, and then it's not going to know what you're doing with your 8. Do caret here? No. 3 caret 8 would not be the same thing. The EE button, again, represents times 10 to whatever number you punch in next. So if I punch in the 8, that's what goes in my N. And 37, is that the answer? Yeah. And that's 37 kilograms. Grams? Oh, so what do we need to do? Here, let's scoot that down a little. So kilograms here, grams there. Which one's bigger? And 1,000. So that means that we're going to have 37